Hello, and welcome to Beyond the Last Star. Wherever you are right now, whatever kind of day it has been, you made it here. And that is enough. Find a comfortable position. Let your body settle. If you can, turn the lights down low or off completely. Because tonight, we are not staying here. Tonight we are going somewhere most people never think to go. Past the last planet, past the edge of the sun's reach, into the deep and patient dark where the real universe begins. Before we leave though, drop a comment and tell me where in the world you are listening from right now and what time it is there. I read every single one. There is something I love about knowing that people from every corner of this small blue planet are drifting off to the same stars at the same moment. And if this is your first time here, welcome home. Hit subscribe so the next journey finds you. Now, are you ready? Let's go. Tonight we are not going to answers. Tonight we are going somewhere more interesting than answers. Tonight we are going to the questions. The ones that have no answers yet. The ones that the best minds in science have been sitting with for decades, sometimes for centuries, still cannot fully resolve. Not because they are not smart enough, not because the instruments are not sensitive enough, but because the universe, it turns out, is stranger and deeper and more surprising than any model we have built to describe it. The questions that remain open in space science are not the embarrassing leftovers of an incomplete project. They are the most honest and beautiful parts of the whole enterprise. They are the places where knowledge ends and genuine mystery begins. And in those places, in the dark between what is known and what is not yet known, there is a particular kind of quiet that is very good for falling asleep to. Dark matter is the most abundant thing in the universe that we have never directly detected. Roughly 85% of all the matter in the cosmos is dark matter. Not dark in the sense of being dim or shadowy. Dark in the sense of being completely invisible, emitting no light, reflecting no light, absorbing no light. It passes through ordinary matter as if it were not there. It passes through you, right now, several times per second, leaving no trace you could ever feel. We know it exists because of what it does to the things around it. Galaxies spin faster than they should if only visible matter were providing the gravitational pull. Galaxy clusters bend light more strongly than their visible mass can account for. The large-scale structure of the universe, the great filaments and voids of the cosmic web, could not have formed in its current arrangement without the gravitational scaffolding of enormous amounts of invisible mass. The evidence for dark matter is overwhelming. But what it actually is, what particle or particles make it up, what forces beyond gravity it responds to, whether it is a single substance or many, remains completely unknown. Experiments deep underground, shielded from all other radiation, have been searching for dark matter particles for decades without a confirmed detection. The most abundant ingredient in the universe is still a mystery. Dark energy is stranger still. In 1998, two independent teams of astronomers were measuring the expansion of the universe, expecting to find that it was slowing down over time. The natural result of gravity pulling everything back toward everything else. Instead, they found the opposite. The expansion of the universe is accelerating. It is speeding up. Something is pushing the fabric of space itself outward at an increasing rate, overcoming the pull of gravity on the largest scales. This something has been named dark energy, and it constitutes roughly 68% of the total energy content of the universe. We do not know what it is. The leading hypothesis is that it is a property of space itself, that empty space has an inherent energy, a cosmological constant that drives the expansion. But the predicted value of this constant from quantum mechanics disagrees with the observed value by a factor of somewhere between 10 to the power of 60 and 10 to the power of 120, the largest discrepancy between theory and observation in the history of physics. Something is profoundly wrong with our current understanding of the relationship between quantum mechanics and cosmology. And dark energy is the place where that wrongness shows itself most clearly. The universe is mostly made of things we do not understand. The origin of the universe's matter is one of the deepest puzzles in all of physics. The Big Bang, according to our best current models, should have produced equal amounts of matter and antimatter. Every particle of matter has a corresponding antiparticle of antimatter, identical in mass but opposite in charge. When matter and antimatter meet, they annihilate each other completely, converting entirely to energy. If the Big Bang produced equal amounts of both, the matter and antimatter should have annihilated each other entirely, leaving a universe of pure energy and nothing else. No atoms, no stars, no planets, no you. And yet here we are. The universe is made of matter. Antimatter exists only in tiny amounts, produced in particle accelerators and cosmic ray collisions, gone almost instantly. Something in the earliest moments of the universe created a slight asymmetry. Roughly one extra particle of matter for every billion particle-antiparticle pairs, and that tiny imbalance is the reason the entire material universe exists. What caused that asymmetry? What broke the perfect symmetry between matter and antimatter in those first fractions of a second? Science does not yet know. The answer, when it comes, will be one of the most fundamental discoveries in the history of physics. The universe is 13.8 billion years old. We know this with remarkable precision. The cosmic microwave background, the faint afterglow of the Big Bang, tells us when the universe became transparent to light, and from that we can calculate its age. But what came before the Big Bang is a question that current physics cannot answer. Not because it is philosophically impossible, but because the mathematics of our best theory of gravity, general relativity, breaks down at the singularity. The equations produce infinities. Infinities in physics equation is a sign that the theory is being pushed beyond its domain of applicability, that a deeper theory is needed. The deeper theory, a quantum theory of gravity that can describe what happened at the moment of the Big Bang and potentially before it, does not yet exist. String theory is one attempt. Loop quantum gravity is another. Neither has yet predictions that can be tested with current instruments. What happened before the Big Bang? What caused the Big Bang? Whether the Big Bang was truly the beginning of everything, or the latest in a series of cosmic events? These remain genuinely open questions. The beginning of everything is still mysterious. The universe appears to be flat. Not flat in the sense of being two-dimensional, but flat in the geometric sense, and the large-scale geometry of space-time appears to be Euclidean, meaning that parallel lines remain parallel. Triangles have angles that add up to 180 degrees, and the universe extends in 3 spatial dimensions without any measurable large-scale curvature. This is one of the most puzzling features of the cosmos, because a perfectly flat universe requires extraordinarily precise initial conditions. Any slight deviation from flatness in the earliest moments of the Big Bang would have been amplified enormously over time, producing either a universe that collapsed immediately or one that expanded so quickly it could never form structure. The standard explanation for why the universe is so close to perfectly flat is cosmic inflation, a period of extraordinarily rapid exponential expansion in the first tiny fraction of a second after the Big Bang, which would have stretched any initial curvature to imperceptibility. Inflation explains the flatness problem beautifully. But what caused inflation? What was the inflationary field? What made it start? And what made it stop? The mechanism behind the most important event in the history of the universe remains unknown. The cosmic microwave background. The faint uniform glow of radiation left over from the early universe is almost perfectly smooth. In every direction you look, the temperature is the same to within 1 part in 100,000 of golden daffodils. This is astonishing, because the early universe was expanding so fast that regions on opposite sides of the sky could never have been in contact with each other. They were separated by distances greater than light could have crossed in the time available. How did they come to be at the same temperature? If two regions have never been able to exchange energy or information, how did they reach thermal equilibrium? This is called the horizon problem, and it is one of the classic puzzles of modern cosmology. Again, inflation provides a possible explanation. If the entire observable universe expanded from a region small enough to be in thermal contact before inflation began, then inflation would have stretched it to cosmic scales while preserving the uniformity. But the mechanism of inflation itself remains unconfirmed. The smoothness of the cosmic microwave background points at an explanation we cannot yet verify. The first 10 stars in the universe are a mystery we are only beginning to resolve. Somewhere between 100 million and 400 million years after the Big Bang, in the period astronomers call cosmic dawn, the first stars ignited in the dark. These stars were made of almost pure hydrogen and helium, with almost no heavier elements, because no previous generations of stars had yet lived and died to create them. They were thought to be enormous, perhaps hundreds of times the mass of our Sun, because without heavier elements the gas clouds could not cool as efficiently, forcing larger and more massive stars to form. They burned brilliantly and briefly, then died in spectacular explosions that scattered the first heavy elements into the universe. But we have never directly observed a population 3 star, as they are called. They formed and died before any surviving stars were born, and they are so far away, in such early epochs, that even our best current telescopes have not definitively detected them. The James Webb Space Telescope is looking. It has found hints. But the first stars themselves remain tantalizingly just beyond the edge of what we can currently see. The nature of black hole interiors is one of the most profound unsolved problems in theoretical physics. We know that black holes exist. Their gravitational effects are unmistakable, and we have imaged the shadow of the event horizon in 2 different black holes. We know what happens at and just outside the event horizon, the point of no return from which nothing, not even light, can escape. But what happens inside? General relativity predicts a singularity at the centre, a point of infinite density where the laws of physics as currently formulated simply break down. But infinity in physics equations is always a sign that the theory has been pushed beyond its limits. A quantum theory of gravity, which would describe physics at these extreme densities, might replace the singularity with something else. A region of extreme but finite density, or something more exotic. We do not know what the interior of a black hole actually is. No information can escape from inside to tell us It remains one of the most perfectly sealed mysteries in all of science. What is in there? What the universe looks like on the other side of an event horizon is genuinely unknown. The universe contains structures far larger than our models predict it should. The largest known structures in the observable universe, the Hercules Corona Borealis Great Wall, a vast supercluster of galaxies stretching roughly 10 billion light years, are so large that according to our standard model of cosmology, they should not be able to exist. The universe has only been expanding for 13.8 billion years. And the speed of light sets a limit on how quickly gravitational effects can propagate to pull structures together. A structure 10 billion light years across simply should not have had time to assemble itself. And yet it is there. Either our measurements of it are somehow wrong, its true extent is smaller than current data suggests, or there is something wrong with our understanding of how large-scale structure forms in the universe. Perhaps dark energy behaves differently at very large scales than current models assume. Perhaps there are physics we have not yet incorporated. The existence of structures too large to explain is a quiet but persistent challenge to the standard model of cosmology, sitting in the data, waiting for a resolution that has not yet arrived. The WOW signal remains the most tantalizing piece of unresolved evidence in the history of the search for extraterrestrial intelligence. On the night of August 15, 1977, a radio telescope called Big Ear at Ohio State University detected a signal so strong and so unusual that the astronomer reviewing the data the next day circled it on the printout and wrote "Wow" with an exclamation mark in the margin. The signal lasted 72 seconds, exactly as long as the telescope's field of view took to sweep past the point in the sky from which it appeared to come. It had the precise characteristics that SETI researchers had predicted an artificial signal from another civilization might have a narrow bandwidth at a specific radio frequency, the 21 centimeter hydrogen line that had long been thought to be the most logical frequency for interstellar communication. It appeared to come from the direction of the constellation Sagittarius. It was the strongest signal Big Ear ever detected, and it was never detected again. Dozens of subsequent observations of the same patch of sky, using the same telescope and more sensitive instruments, have produced nothing. The signal remains unexplained. It was not caused by terrestrial interference. It passed all the tests designed to distinguish local signals from cosmic ones. Natural astronomical sources do not produce signals with those characteristics. What caused it remains unknown. It may have been brief transmissions. It may have been a transmission from a distant civilizations that we happened to catch at exactly the right moment. It may have been a natural phenomenon not yet catalogued. It may never be explained. But it sits in the data more than 40 years later, still without a satisfactory answer. The Pioneer anomaly puzzled scientists for decades. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s, were among the first probes to travel beyond the outer planets. After their flybys, they continued on into the outer solar system, and engineers tracking their positions found something unexpected. Both probes were decelerating slightly more than gravitational models predicted. The effect was tiny but consistent. An additional tiny force seemed to be acting on both probes, pushing them back toward the Sun at a rate that no known physics could explain. For years, the Pioneer anomaly was one of the more intriguing unsolved problems in solar system science, with some researchers wondering whether it reflected new physics. a modification to gravity at very large distances perhaps. Eventually, in 2012, a careful analysis of the thermal radiation emitted by the spacecraft showed that the slightly uneven heat radiation from the probe's own electronics was providing the tiny extra push toward the Sun, entirely accounting for the anomaly. The Pioneer anomaly was solved, but the process of solving it, the years of careful measurement and analysis, the eventual realization that an overlooked physical effect was the culprit, illustrates how science works with anomalous data and serves as a reminder that not every mysterious measurement conceals new physics. The flyby anomaly is not solved. When spacecraft perform gravitational assist maneuvers, swinging past Earth to gain velocity, they sometimes emerge from the flyby, moving slightly faster or slightly slower than orbital mechanics predicts. This effect is small, measurable, only with very precise tracking, and has been observed in multiple flybys by multiple spacecraft. No satisfying explanation has been found. Thermal radiation effects, the kind that explained the Pioneer anomaly, do not account for the flyby anomaly. The pattern of excess or deficit velocity does not match what thermal effects would produce. The effect may be related to the rotation of the Earth, or to some subtle relativistic effect not fully incorporated in the calculations, or to something else entirely. It is a small anomaly in a specific operational context, not a revolutionary challenge to physics. But it is genuine, reproducible, and without a satisfying explanation. The solar system continues to produce small surprises for the people measuring it most carefully. Cosmic rays of the highest energies remain deeply mysterious. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that continuously rain down on Earth from space, travelling at nearly the speed of light. Most cosmic rays have energies that can be explained by known processes. In the galaxy, shock waves from supernova explosions, the powerful magnetic environments near pulsars, and active galactic nuclei. But occasionally, very rarely, a cosmic ray arrives with an energy so extreme that it should not be possible for it to have travelled very far at all. The GZK limit, named after three physicists who independently predicted it in 1966, establishes that protons travelling at near light speed lose energy rapidly by interacting with the cosmic microwave background radiation that fills the universe. A proton with enough energy to exceed this limit can only have travelled a few 100 million light years before losing most of its energy. And yet, particles exceeding this limit have been detected. They arrive from directions that do not consistently point toward any obvious nearby sources capable of producing them. Where they come from, what accelerates particles to energies above the theoretical maximum for distant sources, is unknown. They are called "Oh my God" particles, after the reaction of the first astronomer who calculated the energy of the most extreme one detected. They remain unexplained. The varying speed of light controversy is not mainstream physics, but it is a genuine debate among a small number of serious physicists. The speed of light in a vacuum is one of the fundamental constants of nature. 300,000 kilometers per second, the same everywhere, always. Or so the standard model assumes. A small group of physicists has proposed that the speed of light may have been different in the very early universe, faster, possibly much faster, and that this variation could provide an alternative to cosmic inflation as an explanation for the horizon problem and the flatness problem. This is not accepted physics. The evidence for a varying speed of light is not strong, and the proposal faces significant theoretical challenges, but it has not been definitively ruled out, and some measurements of the fine structure constant, a dimensionless physical constant that depends partly on the speed of light, have shown hints of variation across cosmic time and distance. These hints are controversial and contested. Most physicists regard them as measurement artifacts, but the question of whether the fundamental constants of nature are truly constant, or whether they could vary across the universe or across time, is a genuine open question that touches some of the deepest foundations of physics. The axis of evil is the informal name given to one of the most puzzling features of the cosmic microwave background, when the MAP and Planck satellites mapped the temperature fluctuations in this ancient radiation with extraordinary precision. They found something unexpected on the very largest scales. The largest features in the map, there appears to be a preferred direction. The patterns of hot and cold spots in the microwave background are not distributed randomly across the sky, but show an alignment, a preferred axis, that happens to line up suspiciously well with the plane of the solar system and with the direction of the equinoxes. This alignment should not be there. The cosmic microwave background represents the state of the universe at a time long before the solar system existed. Its large-scale patterns should bear no relationship to the orientation of our local planetary system. And yet, the alignment is there, at a level of statistical significance that is difficult to dismiss as chance. Some researchers believe it is a subtle systematic error in the measurements, a contamination from local structures that has not been fully removed. Others think it may represent a genuine anisotropy in the early universe, a preferred direction baked into the cosmos from its earliest moments. If it is real, it would challenge some of our most basic assumptions about the universe being the same in all directions. The debate continues. The lithium problem is a small but persistent thorn in the side of Big Bang nucleosynthesis theory. In the first few minutes after the Big Bang, the universe was hot enough and dense enough for nuclear fusion to occur in the bulk of the cosmos, not just in stellar cores, but everywhere. This period produced yet the hydrogen, helium, and small amounts of lithium that form the raw material from which the first stars were made. Our theory of Big Bang nucleosynthesis makes precise predictions about how much of each element should have been produced. For hydrogen and helium, the predictions match observations beautifully. For lithium, they do not. The theory predicts roughly 3 times more lithium than is actually observed in the oldest, most pristine stars. The stars that best preserve the primordial chemical composition. Something is wrong. Either the theory of Big Bang nucleosynthesis is incomplete in some way, or the ancient stars have destroyed some of their lithium through processes not fully accounted for, or there is a physical process in the early universe that we have not yet identified. The discrepancy is not enormous, but it is real. It is reproducible, and it points at a gap in our understanding of the first minutes of the universe. The nature of time is one of the deepest puzzles at the intersection of physics and philosophy. At the level of fundamental particles, the laws of physics are time symmetric. They work equally well run forward or run backward, and there is nothing in the equations that distinguishes the past from the future. And yet our experience of time is profoundly asymmetric. Time flows in one direction. The past is fixed and the future is open. Memory works in one direction. Cause precedes effect. Why does time have an arrow if the fundamental laws of physics do not? The standard answer involves entropy. The second law of thermodynamics states that the total entropy of a closed system tends to increase over time from lower entropy to higher entropy, and this provides a direction to time. But this just pushes the question back further. Why was the entropy of the universe so low at the beginning? What set the initial conditions such that the universe started in a low entropy state and has been evolving toward higher entropy ever since? The answer requires understanding the initial conditions of the Big Bang itself, which brings us back to the problem of what happened before, or at the beginning of the universe. The arrow of time and the beginning of the universe are deeply connected mysteries, and neither has a fully satisfying answer. The unexplained infrared excess around certain stars, particularly main sequence stars like Vega and Fomalhaut, was one of the earliest clues that planetary systems might be common in the galaxy. When the IRAS satellite surveyed the sky in infrared light in the early 1980s, it found that some stars were emitting far more infrared radiation than their surface temperatures could account for. The most natural explanation was that these stars were surrounded by disks of warm dust, debris from planetary formation or collisions between planetesimals, that was absorbing starlight and re-radiating it as heat. This interpretation turned out to be correct, and infrared excess is now one of the standard signatures used to identify systems with debris disks, protoplanetary disks, or ongoing planetary formation. But some infrared excesses remain difficult to explain fully. Certain systems show more dust than models of planetary formation and collisions predict. The distribution of dust around some stars is asymmetric in ways that resist easy explanation. The sources of some transient infrared X's, systems where the infrared emission increased suddenly and then faded, remain unknown. Planetary system formation and evolution is an active area of research, and the details of how dust and debris behave around different types of stars in different stages of their evolution still contains real puzzles. The strange dimming of Tabby's star captured public attention and scientific puzzlement in 2015 when citizen scientists participating in the Planet Hunters project noticed that a star designated KIC 8462852, now called Tabby's star, after the astronomer Tabatha Boyajian who led the study, was dimming in ways unlike any previously observed. Normal stellar transits caused by planets passing in front of the star produce smooth, regular, symmetric dips in brightness. Tabby's star showed dips of varying depths, some removing up to 22% of the star's light, with irregular shapes and unpredictable timing. And no known natural process could easily account for all the features of the dimming. Speculation ranged from unusually shaped comets or planetesimal swarms to, in the more colourful media coverage, a megastructure built by an advanced alien civilization. Further study has largely converged on a combination of circumstellar dust clouds and uneven distributions of material around the star as the most likely explanation. But the precise mechanism is still not fully understood, and Tabby's star remains one of the more genuinely unusual stellar objects in the catalogue on the console, Ariel. A reminder that the galaxy contains things that surprise even experienced astronomers. The universe has a missing baryon problem. Baryons are the ordinary particles that make up atoms, protons and neutrons, and they constitute all the visible matter in the universe. Cosmologists can calculate from the cosmic microwave background and from Big Bang nucleosynthesis theory how many baryons the universe should contain. But when they add up all the baryons they can actually find, in stars, in galaxies, in the gas between galaxies, they come up short. roughly half of all the baryons in the universe appear to be missing. They are not dark matter. Dark matter is a different, non-baryonic form of mass, and these are ordinary atoms that should be visible in some form, somewhere, and are not where the models say they should be. The leading hypothesis is that the missing baryons are hiding in the warm-hot intergalactic medium. Thin, diffuse filaments of gas, at temperatures between 100,000 and 10 million degrees Kelvin, stretched across the cosmic web between galaxy clusters, too hot to emit much visible light and too diffuse to be easily detected. This hypothesis has received partial support from X-ray and ultraviolet observations, but the full accounting of the missing baryons has not been completed. Roughly half of all the ordinary matter in the universe is still not confidently located. The universe is hiding its own ingredients from us. Fast radio bursts are among the most energetic and most mysterious phenomena in the observable universe. They are brief, extraordinarily intense flashes of radio waves, lasting only milliseconds, originating from outside the Milky Way, releasing in that fraction of a second more energy than the Sun produces in days or weeks. They were first detected in 2007 when a researcher named Duncan Lorimer found a burst in archival data from the Parkes Radio Telescope in Australia. Since then, hundreds have been catalogued, and some have been found to repeat. The same source producing multiple bursts over time. The repeating sources have been localized to specific galaxies, and their radio signals show the characteristic smearing that indicates they have travelled through enormous amounts of ionized gas, confirming they come from cosmological distances. But what produces them remains unknown. The leading candidates include magnetars, neutron stars with extraordinarily powerful magnetic fields, and mergers of compact objects like neutron stars. Some bursts may have multiple different origins. The repeating sources behave differently from the non-repeating ones, suggesting either different physical mechanisms or different environments. Fast radio bursts are a recent discovery, intensively studied and still poorly understood. A brand new category of cosmic phenomena still being mapped and characterized. The radius problem of neutron stars sits at the boundary between nuclear physics and astrophysics and has resisted resolution for decades. Neutron stars are the collapsed cores of massive stars, objects of roughly solar mass compressed into spheres about 20 kilometers across. The internal structure of a neutron star, what matter looks like at those extreme densities, whether the core contains pure neutrons or more exotic states of matter, depends on something called the nuclear equation of state, which describes how matter behaves under extreme compression. Different equations of state predict different radii for neutron stars of a given mass. Measuring the actual radii of neutron stars would allow us to constrain the equation of state and learn something fundamental about the behavior of nuclear matter. But measuring the radius of an object 20 kilometers across at distances of thousands of light years is extraordinarily difficult. The NASA instrument on the International Space Station has made progress, measuring X-ray pulses from rotating neutron stars to constrain their shapes. The merger of two neutron stars detected in gravitational waves in 2017 provided additional constraints, but the equation of state of neutron star matter remains uncertain, and with it the answer to what the universe's most dense objects are actually made of in their cores. The origin of magnetic fields in the universe is not well understood. Magnetic fields are everywhere, in planets, in stars, in galaxies, in galaxy clusters, and in the intergalactic medium. They play important roles in star formation, in the acceleration of cosmic rays, in the evolution of galaxies, and in many other astrophysical processes. But where did these fields come from? The universe at the time of the Big Bang had no magnetic fields of any significance. Something generated them, amplified them, and spread them through cosmic structures over the history of the universe. Various mechanisms have been proposed. The Biermann battery effect in the early universe, the amplification of tiny seed fields by turbulence and dynamo processes in galaxies and stars, but the precise origin of the first magnetic fields, the seeds from which all subsequent cosmic magnetism grew, is not known, and the magnetic fields observed in the intergalactic medium, the thin diffuse gas between galaxies, are particularly puzzling. They are stronger than most models predict, suggesting either that the seed fields were stronger than expected, or that amplification processes are more efficient than our models account for. The magnetic universe has a history that is not yet written. The age crisis in cosmology is a quiet but real tension in our understanding of the universe. There are two primary ways to measure the age of the universe. The first is from the cosmic microwave background, the afterglow of the Big Bang, which encodes information about the expansion history of the universe and, with a model, allows calculation of its age. The second is from measuring the current expansion rate of the universe directly, using observations of distant supernovae, FEPFIT variable stars, and other distance indicators. These two methods should give the same answer. They are measuring the same universe. But they do not quite agree. The value of the Hubble constant, the number that describes how fast the universe is currently expanding, comes out slightly different depending on which method you use. The discrepancy, known as the Hubble tension, is small but statistically significant, and it has grown more troubling as both measurements have become more precise. If the discrepancy is not a systematic error in one or both measurements, and careful researchers have been unable to find one, it might indicate that the standard model of cosmology is missing something. Some new physics, some ingredient in the early universe not currently accounted for, might be needed to reconcile the two measurements. The Hubble tension is one of the most actively debated problems in cosmology. The nature of quantum gravity is the deepest theoretical problem in fundamental physics. General relativity. Einstein's theory of gravity describes the behavior of space-time on large scales with extraordinary precision. Quantum mechanics describes the behavior of matter and energy on small scales with equal precision. Together, they form the foundation of almost everything we understand about the physical world. But they are amphidils. They are fundamentally incompatible. They use different mathematical frameworks. They make different assumptions about the nature of reality. And when you try to apply both simultaneously, as you must in situations of extreme density and small scale, like the interior of a black hole or the moment of the Big Bang, the equations break down, producing infinities and contradictions. A theory of quantum gravity, a framework that unifies general relativity and quantum mechanics into a single consistent description, is the most sought-after goal in theoretical physics. String theory is one attempt. Loop quantum gravity is another. Neither has yet produced testable predictions different from those of the existing theories. The unification of our two most successful physical frameworks remains the great unfinished project of physics, and without it, some of the most fundamental questions about the universe. What happens at the centre of a black hole? What happened at the very beginning cannot be answered. The solar neutrino problem was one of the longest-running mysteries in astrophysics before its eventual resolution, and its solution opened a new mystery. Neutrinos are nearly massless particles produced in enormous numbers by the nuclear reactions in the Sun's core. For decades, physicists built detectors deep underground and counted solar neutrinos. The results consistently showed far fewer neutrinos than theory predicted. Either the theory of how the Sun generates energy was wrong, which seemed unlikely given how well it matched other solar observations, or something was happening to the neutrinos on their way to Earth. The resolution came with the discovery of neutrino oscillation. Neutrinos can change from one type to another as they travel, and the early detectors were only sensitive to one type. When detectors sensitive to all types were built, the count matched theory perfectly. The solar neutrino problem was solved, but the solution required that neutrinos have mass. Even a tiny amount of mass, but mass nonetheless. The standard model of particle physics in its original form predicted massless neutrinos, so the solution to the solar neutrino problem broke something else. It told us the standard model was incomplete, the exact masses of the three types of neutrinos, and why those masses are so extraordinarily small compared to other particles remains unknown. The mystery of neutrino mass is now one of the open frontiers of particle physics. The great silence, the absence of detectable signals from other civilizations, remains the central puzzle of astrobiology. The Milky Way is 10 billion years old. It contains hundreds of billions of stars. Many of those stars have planets in habitable zones. Even if the probability of life arising on a Kapitalsund or arising on a planet Ultras undeploret is very small, the sheer number of opportunities across such a long history suggests that life should have arisen many times. And if even a small fraction of those origins led to technological civilizations, some of those civilizations should have had millions of years longer than us to develop technology. The galaxy should be full of evidence of intelligence, signals, artifacts, megastructures, something. We detect nothing. The radio sky is quiet. The solar system shows no signs of visitation. This is the Fermi paradox, and it has no satisfying answer. The possibilities range from disturbing to comforting, depending on your perspective. Perhaps life is extraordinarily rare, and we are alone or nearly so. Perhaps civilizations arise but consistently destroy themselves before becoming detectable. Perhaps interstellar travel and communication are so difficult that no civilization has managed them. Perhaps we are not looking in the right way. Perhaps advanced civilizations communicate in ways we have not thought to look for. The silence is data, but it is data without a clear interpretation. Gravitational wave astronomy has opened a new window on the universe, but it has also created new puzzles. The first detection of gravitational waves in 2015 confirmed Einstein's century-old prediction and launched a new era of observation. Since then, the LIGO and Virgo detectors have recorded dozens of merger events. Black holes and neutron stars colliding in distant galaxies. But some of these events have produced surprises. A merger event in 2019 involved a compact object in the mass gap. The range of masses, between about 3 and 5 solar masses, where neither neutron stars nor black holes were expected to exist based on our models of stellar evolution. Another event involved a black hole merging with an object that was either an unusually massive neutron star or an unusually light black hole. The boundaries between neutron stars and black holes, once thought relatively clear, have become blurrier with each new detection. What fills the mass gap? How compact objects form in that range? And what the final states of neutron star mergers look like? are questions that gravitational wave astronomy is only beginning to answer. The origin of the Moon is known in broad outline. A Mars-sized body called Theia collided with the early Earth about 4.5 billion years ago, and the debris of that collision coalesced into the Moon. But the details of this story are still being worked out, and some of them are surprising. The Earth and the Moon have nearly identical isotopic compositions. The ratios of different isotopes of oxygen, tungsten, and other elements are almost indistinguishable between the two bodies. In a simple collision model, you would expect the Moon to be made primarily of Theia's material, which should be different from Earth's, unless Theia happened to form in the same part of the solar system as Earth. The similarity of their compositions requires either that Theia was nearly identical to Earth chemically, which requires an unlikely coincidence, or that the collision was more violent and complete than standard models assume, thoroughly mixing the materials of both bodies. Some researchers have proposed that the collision was so energetic that both Earth and the impactor were vaporized into a rapidly rotating cloud of rock vapor, which then cooled and differentiated to form the Earth-Moon system. The details of how our nearest companion formed, and why it is so similar to us in composition, remain actively debated. The question of whether the universe is finite or infinite remains genuinely open. The observable universe, the region from which light has had time to reach us in the 13.8 billion years since the Big Bang, has a definite size, a sphere about 93 billion light-years in diameter. But the observable universe is not the same as the total universe. The total universe could extend far beyond what we can observe. It could be finite, curving back on itself, like the surface of a sphere in some higher dimensional sense, so that if you could travel far enough in any direction, you would eventually return to where you started. Or it could be infinite, extending without limit in all directions, containing an infinite number of galaxies and stars and planets. Current cosmological observations are consistent with both possibilities. The universe appears to be flat on large scales, neither positively curved like a sphere, nor negatively curved like a saddle. But a flat universe can be either finite or infinite depending on its topology. We have no way to observe beyond the cosmic horizon, no way to detect the curvature of the universe on scales larger than what we can see. Whether we live in a finite or an infinite universe is a question that may never be answerable from within it. The multiverse hypothesis. The idea that our universe is one of many, perhaps infinitely many, universes with different physical properties is taken seriously by some of the most prominent physicists in the world and dismissed by others as metaphysics rather than science. In some versions of inflationary cosmology, the rapid expansion of the early universe does not end everywhere at once, but continues in different regions, creating an eternal inflation of bubble universes, each with potentially different physical constants and laws. String theory, one of the leading candidates for a theory of quantum gravity, predicts an enormous landscape of possible vacuum states, each corresponding to a different universe with different properties. If either of these frameworks is correct, our universe, with its specific values of physical constants, its specific particle content, its specific laws, is just one possibility among an almost unimaginable number. The multiverse would explain why the physical constants of our universe seem fine-tuned for the existence of complex structures and life. In an infinite multiverse, we would of course find ourselves in one of the universes compatible with our existence. But the multiverse cannot be tested. Other universes, if they exist, are by definition beyond our observational reach. Whether the multiverse is a genuine scientific hypothesis or an untestable philosophical extension of physics remains a live and unresolved debate. The fine-tuning problem sits at the heart of one of the deepest puzzles in physics and cosmology. The fundamental constants of nature, the strength of gravity, the mass of the electron, the strength of the electromagnetic force, the cosmological constant, appear to be set to values that allow complex structures like atoms, molecules, stars, planets, and life to exist. Small changes in any of these values would produce a universe radically different from ours. One that might collapse immediately after the Big Bang, or expand so fast that matter never clumps together, or lack the nuclear physics necessary to produce heavy elements. The universe appears finely tuned for complexity. Why? One answer is the multiverse. In an infinite space of possible universes, ours is simply one of the rare ones compatible with our existence. Another answer is that we are missing a deeper theory that explains why the constants have the values they do, that what appears to be fine-tuning will turn out to be the inevitable result of some deeper physical principle not yet discovered. A third answer considered by some philosophers and physicists involves the role of conscious observers in the selection of physical parameters. None of these answers is fully satisfying. The fine-tuning problem remains one of the most profound unsolved puzzles at the boundary of physics and philosophy. The corona of the Sun is hotter than its surface, and nobody fully understands why. The surface of the Sun, the photosphere, has a temperature of about 5,500 degrees Celsius. As you move away from the surface, you might expect the temperature to drop, the way it drops as you move away from any heat source. Instead, it rises dramatically. The solar corona, the outermost layer of the Sun's atmosphere, extending millions of kilometers into space, has a temperature of 1 to 3 million degrees Celsius, hundreds of times hotter than the surface below it. This violates what seems like obvious physical intuition. Something is depositing enormous amounts of energy into the corona, heating it to temperatures far above what direct radiation from the surface could account for. The leading candidates are Ulthuan waves, oscillations in the solar magnetic field that carry energy from the surface into the corona and dissipate it as heat, and nanoflares, tiny magnetic reconnection events too small to observe individually, but collectively releasing enormous amounts of energy. Both mechanisms probably contribute, but the precise physics of coronal heating, the relative importance of different mechanisms in different regions of the corona, and why the corona maintains such extreme temperatures remain incompletely understood. The star that warms our world has a hot mystery sitting above its surface. Mars had water. This is not in serious dispute. The evidence is overwhelming. Ancient river valleys, lake beds, delta deposits, sedimentary rock laid down in standing water, minerals that form only in the presence of liquid water, traces of ancient shorelines. For hundreds of millions of years, or possibly longer in the deep past, Mars had liquid water on its surface, which means it had a thicker atmosphere and a warmer climate than it has today. Then something changed. The water disappeared, the atmosphere thinned, the climate turned cold and dry and hostile. What happened to Mars is one of the most consequential questions in planetary science, not just for what it tells us about the history of Mars, but for what it might mean for the history of life there, and for what it tells us about the fragility of planetary habitability in general. The leading explanation involves the loss of Mars's global magnetic field, which left the atmosphere unprotected from the solar wind, which then slowly stripped it away. But the timing and details of this process, the role of volcanic activity and giant impacts in the climate transition, and the question of whether any subsurface water remains in liquid form today are still being actively investigated. Mars is a cautionary tale written on another planet, and we are still reading it. The rings of Saturn are young. This was one of the most surprising findings of the Cassini mission, which spent 13 years orbiting Saturn and measuring everything it could about the ring system. For decades, the assumption had been that Saturn's rings were ancient, remnants of the material left over when the solar system formed, perhaps 4.5 billion years old. But Cassini's measurements of the mass and composition of the rings, combined with measurements of how quickly they are losing mass to the planet through a process called ring rain, suggest that the rings are far younger. Perhaps only 10 to 100 million years old. The dinosaurs may have still been alive when Saturn's rings formed. This raises an obvious question. Where did the rings come from? Something had to be torn apart to create a ring system of this mass and composition. A large moon, perhaps, disrupted by tidal forces or a collision, or a comet that wandered too close. The identity of the progenitor body and the precise mechanism of its destruction are unknown. Saturn's most iconic feature, the structure that defines the planet for every human who has ever looked at it through a telescope, may have formed quite recently in geological terms, and its origin is not yet understood. The shape of the universe's largest structures challenges the standard model. The cosmic web, the large-scale structure of the universe, in which galaxies are arranged along vast filaments connecting nodes of dense galaxy clusters surrounding enormous empty voids, is predicted by simulations based on the standard model of cosmology, and generally matches what is observed. But on the very largest scales, some observations suggest anomalies. The Sloan Great Wall, the Hercules Corona, Borealis Great Wall, and other enormous structures are larger than standard cosmological models comfortably accommodate. The universe appears to be homogeneous, the same in all directions, on the largest scales, as the standard model predicts. But the evidence for homogeneity at the very largest scales is not as strong as it is at intermediate scales. Some researchers have suggested that the universe may have large-scale flows, regions where galaxies are moving together in ways that exceed what the standard model predicts, driven by unseen mass concentrations beyond our observational horizon. The evidence for these dark flows is contested, but the behaviour of the universe on the very largest scales, beyond the cosmic horizon of our most complete surveys, is genuinely uncertain. The nature of consciousness. The nature of consciousness and its relationship to the physical world that space science owns, but it becomes relevant when asking about the possibility of life elsewhere in the universe. If consciousness is simply what complex information processing feels like from the inside, a property that emerges from sufficiently complex physical systems regardless of their specific substrate, then it might arise in many different forms, in many different chemical and physical environments. If consciousness requires something more specific, particular kinds of chemistry, particular evolutionary histories, particular physical substrates, then it might be rarer, or might look very different in different environments. The question of whether a sufficiently complex network of silicon could be conscious, The way a sufficiently complex network of neurons is conscious is not settled. The question of what physical or informational properties are necessary and sufficient for conscious experience, the hard problem of consciousness, is not solved. This matters for astrobiology, because what we mean when we ask whether life exists elsewhere depends partly on what we think consciousness requires. The search for life elsewhere is also quietly, a search for something we do not fully understand about our own inner experience. The fate of the universe on the very longest timescales depends on the nature of dark energy, which remains unknown. If dark energy is a cosmological constant, an intrinsic property of empty space that does not change over time, the universe will continue expanding forever, growing cold and dark as stars burn out and galaxies drift apart. In the far future, black holes will evaporate through Hawking radiation, protons may decay, and the universe will approach a state of maximum entropy. The heat death, where no more useful energy is available and all processes cease. This is the most commonly discussed fate. But if dark energy is a dynamic field that changes over time, different fates are possible. If the field grows stronger, the expansion of the universe could accelerate catastrophically, eventually tearing apart galaxies, then stars, then planets, then atoms, in a scenario called the Big Rip. If the field weakens or reverses, gravity could eventually overcome the expansion, causing the universe to contract in a big crunch. The eventual fate of everything depends on the nature of something we have not identified. The universe is holding its own ending in something we cannot see. The existence of life on Earth is not fully explained. The origin of life, the transition from chemistry to biology, from non-replicating molecules to self-replicating systems capable of evolution, is one of the deepest unsolved problems in all of science. We know that life on Earth began at least 3.5 billion years ago, possibly earlier. We know that the building blocks of life, amino acids, nucleotides, lipids, can form under conditions thought to have existed on the early Earth, and have been found in meteorites and synthesized in laboratory simulations of early Earth conditions. But the specific sequence of steps by which these building blocks assembled into the first self-replicating molecule surrounded itself with a membrane, and began the process of Darwinian evolution. That sequence is not known. Dozens of hypotheses have been proposed. Some favour deep-sea hydrothermal vents as the cradle of life. Others favour shallow tidal pools subjected to cycles of wetting and drying. Some invoke the RNA world, where RNA molecules served as both information carriers and catalysts before the division of labour between DNA and proteins evolved. None of these hypotheses is fully verified. The origin of life, the most important event in the history of this planet, the event that made everything that followed possible, including the asking of this question, remains genuinely mysterious. The questions are quieter now, not less real, every one of them as genuine and as open as when this began, but quieter, the way all things grow quieter, when the night has been long enough and the mind has travelled far enough that it no longer grips them. The questions are still there. They will still be there tomorrow, and there is something deeply restful about that. About the fact that the universe keeps its mysteries carefully, tending them across billions of years, never in a hurry to resolve them. Patient, in a way that nothing with a heartbeat can quite manage. The water on Earth may have come from space. Earth formed in a region of the solar system too hot for water ice to have been a significant component of the original material, and yet the Earth has oceans. Vast, deep, life-bearing oceans covering most of the planet's surface, providing the medium in which life arose and evolved. Where did all this water come from? The leading hypothesis involves delivery by asteroids and comets from the outer solar system, where water ice was stable and abundant, impacting the early Earth during a period of intense bombardment roughly 4 billion years ago. But the details of this hypothesis are not settled. The isotopic composition of Earth's water, the ratio of ordinary hydrogen to deuterium, a heavier form of hydrogen, matches the water in certain classes of asteroids better than it matches the water in comets, suggesting asteroids played a larger role. But not all asteroid classes match perfectly, and the timing and intensity of the late heavy bombardment, the period of intense impacting, is still debated. The origin of Earth's oceans, the specific sources, the timing, the processes, is not fully resolved. The water that makes this planet habitable arrived from somewhere, and the full story of how it got here is still being assembled. The magnetic field of Mercury is a puzzle that planetary scientists have not fully resolved. Mercury is a small planet, only slightly larger than our Moon, and small rocky bodies generally lack global magnetic fields because their interiors cool quickly, solidifying the liquid metallic layers whose motion generates magnetic fields through the dynamo effect. Earth has a global magnetic field because it has a large molten metallic outer core still in motion after 4.5 billion years. Mercury, being so much smaller, should have cooled much faster and lost its magnetic field long ago, and yet it has one. Weak, about 1% the strength of Earth's field, but measurably global and clearly generated by an internal dynamo process. How Mercury has maintained a partially liquid core and an active dynamo for billions of years, despite its small size, is not fully understood. High concentrations of sulfur or other light elements in the core might lower its melting point, keeping more of it liquid. Tidal forces from the sun might provide additional heating. The precise mechanism is uncertain, and Mercury's magnetic field remains one of the unresolved puzzles of inner solar system geology. Exoplanet atmospheres are yielding their secrets slowly and incompletely. The James Webb Space Telescope has transformed our ability to characterize the atmospheres of planets around other stars, detecting carbon dioxide, methane, water vapor, and other molecules in the atmospheres of planets hundreds of light years away. This is extraordinary progress by any measure, but enormous gaps remain. The atmospheres of most known exoplanets have not been characterized at all. They are known to exist by the way their host stars wobble or dim, but nothing is known about what they contain. Of the atmospheres that have been studied, many show features that do not match our models. Clouds at unexpected altitudes, temperature structures that disagree with predictions, chemical abundances that require explanations not yet provided. The diversity of planetary atmospheres in the galaxy appears to be far greater than anything in our solar system suggested. And our theoretical framework for understanding that diversity is still in early development. Every new atmospheric measurement from Unjobustiest adds to a picture that is becoming richer and stranger and more complicated. And the comprehensive understanding of how planetary atmospheres form, evolve, and maintain themselves across the vast range of conditions found in the galaxy is a project that will occupy astronomers for decades. The internal structure of gas giant planets remains imprecisely known. Jupiter and Saturn are the largest planets in our solar system, and we have been studying them for centuries with telescopes and more recently with dedicated spacecraft. But what lies beneath their visible cloud layers? The detailed structure of their interiors. the composition of their cores, the behavior of hydrogen under the extreme pressures found deep inside, is known only approximately. The Juno spacecraft, currently in orbit around Jupiter, is providing unprecedented measurements of the planet's gravitational field, which constrains its internal structure. The results have already surprised researchers. Jupiter's core appears to be diffuse rather than compact, suggesting it may have been eroded or diluted by convective mixing over billions of years, or that it never fully differentiated in the first place. Saturn's interior is similarly uncertain. The transition between molecular hydrogen and metallic hydrogen, the depth and composition of any solid or liquid core, the precise density profile with depth. These remain incompletely known for both planets. Understanding the interiors of the giant planets matters not just for our own solar system, but for understanding the enormous population of giant exoplanets discovered around our other stars, most of which cannot be studied in comparable detail. The geysers of Enceladus are among the most exciting phenomena in the solar system, but their precise mechanism is still debated. Saturn's moon, Enceladus, vents water vapour and ice particles from cracks near its south pole in tall plumes that feed material into Saturn's E ring. The Cassini spacecraft flew through these plumes multiple times, detecting water, salt, organic molecules, molecular hydrogen, and silica nanoparticles, evidence that strongly suggests liquid water in contact with warm rock on the floor of an internal ocean. The molecular hydrogen in particular is consistent with Stetson with serpentinization, a chemical reaction between water and certain kinds of rock that also produces heat and is thought to be one of the possible energy sources for life in hydrothermal systems on Earth. The conditions inside Enceladus appear to be, by our best current understanding, potentially habitable, but the details of the plume mechanism, exactly how water from the internal ocean reaches the surface, what drives the episodic activity, whether the cracks are fed directly from the ocean or from a near-surface reservoir, are not fully resolved. Enceladus is one of the most compelling targets for the search for life in the solar system, and many of the most important questions about it are still open. The long-term stability of the solar system is not guaranteed. The orbits of the planets in our solar system are stable over short timescales, stable over millions of years, stable enough for life to have developed and persisted on Earth. But computer simulations of the solar system extended over billions of years reveal that the orbits of the inner planets are chaotic on very long timescales. Chaos, in this context, does not mean random. It means sensitive to initial conditions, so that tiny differences in starting positions amplify over time into large differences in eventual trajectories. Some simulations show that over timescales of billions of years, there is a small but non-negligible probability that the orbit of Mercury could be perturbed, potentially leading to a collision between Mercury and Venus, or between Mercury and the Sun, or, in rare scenarios, to interactions that could disrupt the orbits of the other inner planets. The Earth is not at serious risk in any currently computed scenario for the remaining lifetime of the Sun. But the solar system is not the clockwork of eternal regularity it once appeared. On billion-year timescales, it is a dynamical system with genuine uncertainty in its future. The composition of interstellar dust is incompletely known. Dust grains in the interstellar medium, tiny particles of carbon, silicates and ices, play crucial roles in astrophysics. They provide the surfaces on which molecular chemistry occurs, converting atomic gas into molecular clouds. They shield the interiors of dense clouds from ultraviolet radiation, allowing complex molecules to accumulate. They scatter and absorb light, producing the reddening of distant stars and the dark patches in the Milky Way. They carry organic molecules, including amino acid precursors, through the galaxy. But the detailed composition of interstellar dust, the specific mix of minerals, the size distribution of the grains, the precise nature of the carbonaceous component, is not fully characterized. Spectroscopic observations reveal certain features that are attributed to specific chemical bonds in the dust, but not all the observed spectral features have been matched to identified compounds, the unidentified infrared bands. A set of emission features seen in interstellar dust illuminated by ultraviolet radiation were mysterious for decades before being attributed to polycyclic aromatic hydrocarbons. But this assignment is still not entirely certain. The interstellar medium is a chemical environment more complex than any laboratory, and its complete chemistry is not yet mapped. The question of whether there are other universes is unanswerable with current physics. But it is a genuine scientific question, rather than mere speculation. The word universe originally meant everything, the totality of all that exists. But in modern cosmology, it is often used in a more restricted sense, referring to the observable universe or to our particular space-time. Some theories, eternal inflation, string theory's landscape, the many worlds interpretation of quantum mechanics, suggest that what we call our universe is not all that exists, that there are other regions of space-time, other sets of physical laws, other histories. These other universes are by definition unobservable from within our own. No signal can pass between them, no experiment can probe them, but their possible existence is a logical consequence of theories that are supported by other evidence. Whether to take seriously the existence of things that are in principle unobservable is a genuine philosophical and methodological question for science. The boundaries of what counts as a scientific hypothesis, testable, falsifiable, subject to empirical constraint, are themselves being renegotiated at the edges of cosmology and quantum mechanics. The question of other universes is not science fiction. It is a frontier where physics and philosophy are trying to sort out their boundaries. The silence settles now, not the silence of questions resolved or mysteries closed, the silence of a mind that has held, for a time, the shape of the unknown, the genuine, verified, carefully studied unknown that exists at the edges of our best science. Every mystery described tonight is real. Every gap in understanding is genuine. Every open question is being worked on by people with extraordinary instruments and extraordinary patience, adding measurement by measurement to the vast and growing body and in the process of what is known, and discovering that the boundary of the unknown is larger, not smaller, than it appeared before they started. This is what science actually is. Not a collection of settled answers, but a living relationship with the edges of knowledge, not a finished picture, but a continuously refined sketch. Each revision more accurate than the last, and each accuracy revealing new details that the previous sketch was too crude to show. The universe is larger than our models, stranger than our expectations, more full of genuine surprise than any century of discovery has been able to exhaust. And every question that remains open is an invitation to look more carefully, to build better instruments, to think more clearly, to sit with the uncertainty long enough that the shape of the answer begins to emerge from the dark. The dark matter is still there, flowing through you, through the room, through the planet, as it always has. The fast radio bursts are still firing in distant galaxies, since brief and brilliant and unexplained. The WOW signal sits in a drawer in a university archive, its source still unknown. The nearest star is burning 4.2 light-years away, orbited by a world whose atmosphere we have not yet characterized. The universe is expanding faster than it should be, for reasons we do not understand, in a direction no one predicted 30 years ago. The origin of life, the nature of consciousness, the fate of the cosmos, all open, all real, all patient. The questions do not need you to hold them tonight. They have been held for decades by people whose lives are organized around them. They will be held tomorrow by the next generation of those people. They will remain open for as long as it takes, which may be years or decades or centuries, or which may be answered next Tuesday by a graduate student who looks at old data in a new way and sees something everyone else missed. The universe gives up its secrets on its own schedule, not ours. And you can rest in that. You can lie in the dark and let the questions float at their proper distance, enormous and patient, and not requiring anything of you tonight. The dark matter flows through you in silence. The cosmic microwave background touches you from every direction at just barely above absolute zero. The light from Proxima Centauri is 4 years into its journeys to instruments that will one day read it carefully. Somewhere in a distant galaxy, a fast radio burst has just fired, and its signal is now crossing the universe at the speed of light, headed toward a detector that does not yet exist. Carrying its mystery at 300,000 kilometers per second through the dark, everything is still going. Everything is still open. The universe has been running for nearly 14 billion years without running out of surprises, and there is no sign that it plans to start now. The questions will be here tomorrow. The mysteries will deepen before they resolve. The sky above you will hold the same stars, each one a sun, each one a possible centre of something, each one carrying its own unresolved story. In the light it sends outward in all directions, patient and indifferent and beautiful. Rest now. The universe keeps its own watch, and tomorrow night there is more. Deeper questions, stranger phenomena, the places where the known world gives way entirely to something that has not yet been named. The story of what science cannot explain is also the story of what it is still becoming. And it is nowhere near finished.